And within the review committee, we have also former president of SPIE, Małgorzata Kujawińska. And we organized 4 years ago a Congress on Optics of Electronics. Similar Congress will be organized probably in 2 years in Krakow, so second Congress, by our society. And what I brought to you is a new journal, peer-reviewed journal on the Photonics of Poland, known Photonics Letters of Poland. Already 2 numbers have appeared, so it is quarterly. So you have the contents of these 2 numbers, and the International Advisory Board, they are renowned scientists in the field. As you can recognize here, Phil Russell, Professor Phil Russell is also at this board international, dealing with optics, photonics of electronics. So if you will something interesting for 3 pages to publish, so we have free access, so we don't you don't need to pay for authors, either for readers. So it is for first 5 years in such a way. And the background, because somebody asked me, was it a famous Polish physicist or optics? So I would say at my university is a table of Mieczysław Wolfke, Professor Mieczysław Wolfke. Probably nobody knows, as it is in cases, in the case of liquid crystals or the case also of others, that the Denis Gabbard, who was granted a Nobel Prize for inventory of holography, was based on the works of Mieczysław Wolfke, published in 20s, so about 25 years ago, before the Gabbard work appeared. And in his speech, in Nobel Prize speech, Gabbard said that he hadn't knew about these works, although he just discovered that the Wolfke and also Zernike were the predecessors or precursors of holography. So it is as an introduction, and now we will go to the subject of my today's talk. Okay, so today I will continue the topic of photonic liquid crystal fibers, and I'm very grateful to Professor Russell for a very nice set of lectures, so that illuminated me with new ideas how to use photonic crystal fibers in collaboration with liquid crystals. And first, my set of lectures was devoted to fundamentals. So I spoke about the fundamentals of liquid crystals, few words about photonic crystal fibers in view of coupling of merging possibilities. And today I would like to keep your attention mostly to very spectacular polarization phenomena in these fibers, which we have been investigating for the last few years. Of course, as usual, in such a presentation, I will just review, make you familiar with some basic principles of polarization phenomena in fibers, and how we have been gone our way from to looking for polarization effects in the photonic crystal fibers infiltrated with liquid crystals. Then I will just show you results on the properties of polarization properties of the highly birefringent photonic liquid crystal fibers, tuning properties mostly, and also polarization and depolarization, because it is very closely related. At the end, I have added the hot topic of our today's research, which was never been published, only submitted a few days ago to Optics Express, is under consideration, on high-index glass-based photonic liquid crystal fibers. And some applications, some also possibilities of application, because they are brand new devices or structures, will end this talk. Well, just to very beginning on polarization phenomena in optical fibers. So very short history of polarization. First mention about polarization was devoted to Huygens in the 17th century, but as a matter of fact, in French physicist Malus just defined the polarization, and the law Malus is well known. In this fundamental book, Principles of Optics, which was written by Nobel Prize Born and Emil Wolf, his young collaborator before World War II. It was originally written in German optic and then translated by Wolf, who has been still for more than 40 years active in the field and make a lot of addition on this book. So the issue of polarization was very nicely presented. So probably some of you know this book, so the latest edition, and you will find a lot of information about the polarization, coherence, ondulation, partial polarization, so for the first time mentioned in the book. In the terms of fibers, so the so-called polarizations appeared in early 70s, 1971. Glock introduced the concept of linearly polarized modes. And based on this first experimental demonstration of polarization properties of fibers is attributed to the work of APL, Kaminov, and Ramaswamy in 1979. So the 80s were devoted to exploration of new types of anisotropic fibers, as it was known, highly birefringent polarization maintaining fibers. Mostly it was driven by telecommunication because it was interest for coherent transmission, but also at that time the idea of sensing appeared with these fibers. In the 90s there was the issue of polarization mode dispersion, which limited the bitrate of telecommunication lights, so these contents of polarization within the fibers reappeared in a great scale for the telecommunication people. And since that, telecommunication people started to collaborate in physicists dealing with sensing application of polarimetric sensors. So, and end of the 90s, that was first fiber liquid crystal demonstrated, which was a property of single polarization guiding. In terms of, in the field of photonic crystal fibers, the polarization maintaining fibers, high binding fibers, first demonstrated by place photonics by a group of Professor Russell, about 2000, precisely there is in publication. And in the, when infiltrating fluid crystals, the idea of polarization preserving and birefringence appeared only a few years ago. There's a lecture description of polarization of light, and you can describe in different manner polarization ellipse as usual, but also to treat the polarization totally, you should introduce Stokes vector, which is composed of 4 Stokes vector parameters. And the Stokes vector approach deals also with the situations, general situations in bulk space, not only fibers, also fibers, of the diminution of polarization, so we call effect of depolarization. And the degree of polarization, DOP, is defined in terms of Stokes vector parameters. Whereas when we deal with highly birefringent polarization maintaining fibers, since the beginning of 80s, so more than 25 years ago, nearly 30 years ago, a lot of different structure appeared. So from the very beginning, there are two structures which appeared simultaneously commercially. That was a bowtie fiber in UK and panda fiber in Japan. And also some constructions with elliptical core or elliptical cladding. And of course, at the end of about 10 years ago, appeared the different types of photonic crystal fibers. In these terms, also the elliptical core fiber made of liquid crystals appear to have nice polarization properties. Applications of this fiber from very beginning for coherent transmission were replaced by specific types of polarimetric fiber optic sensors, and also nowadays are compensators for high-speed systems more than 10 gigabits. These phenomena are reviewed in the paper Progress in Optics published 9 years ago, about a decade ago. So the principle, not including photonic crystal fibers, because at that time they have been not well known. what is the origin of polarization phenomena in fibers? So, based on the model of the approach, Glock approach, we can identify, well, just real modes, HE, hybrid modes, and EH modes, that can separate into the scalar wave equations, and they are, of course, definitions, literature definition, textbook definitions of these two modes. But the lowest order mode in the exact solution of the Maxwell equation that is given by Hondros divide, it is HE11 mode. And in this mode, we can distinguish two fields. So in this mode, although it's hybrid mode, there are transverse fields X and Y which dominate the longitudinal EZ field, and that is why we can attribute two polarizations connected with these two fields in direction X and Y. So this is the cutoff frequency which distributes the limit between the single mode and two mode or higher modes. When Glock introduced the LP modes, linear polarized mode, he made an approximation, so-called weak guiding approximation, that the refractive index of the core is slightly higher than the refractive index of cladding. So in that terms, it corresponds to this delta n infinity in the lecture of Professor Russell, higher than 0. And he attributed the second order modes decomposed to the composition of real modes of the fiber, and some, for example, if we have a second order special LP modes, LP11, it can have two polarizations, but also two orientations, two spatial orientations of the field. So either even or odd orientation with two polarizations. So altogether, second order modes is decomposed of 4 separate modes. And if we have an isotropic fiber, these modes are generated. So it means we cannot distinguish because they have the same speed of propagation, so propagation vector. What will be done if we have a highly birefringent fibers? Highly birefringent fibers lifts this degeneration, and for example, if we have a single mode regime, so below normalized frequency 2.4, we will have a separation of the propagation constants of X and Y polarization, say, and the level of this separation is a measure of a birefringence of the fiber. So this is delta beta, so it's a measure of a birefringence of the fiber. The same happens when we have a second order mode, LP11. It will separate also of course, in this second order regime, we have always first single mode, and the second order even and then odd appear. In this view graph, we have shown here the even mode. So it means that for specific wavelengths, we can have, instead of 2, either 4 or 6 separate degenerated modes which have different propagation constants. The measure of this is a parameter which can be easily measured at visible wavelengths. It's a bit-length parameter, LB. It is inversely proportional to the measure of birefringence to the delta beta. So in high bi fibers, this parameter can reach, in classical high bi fibers, level of 1 millimeter. However, in PCF fibers, so photonic crystal fibers, the parameter is about 10 times lower. So it means birefringence is 10 times higher. So, and this is exactly the difference of propagation constants related to the measure of birefringence. Birefringence, as traditional measure, is a difference between refractive, effective, and refractive indices of the modes. To describe polarization properties of the fiber, under the condition that the input light is totally polarized, we use John's formalism. So the fiber itself behaves like a transmission matrix, which depends on wavelength and, of course, an environment X. And the fiber is a device, it's a black box that transmits input to output field. This black box can be decomposed into three parameters: amplitude, phase, and Jones birefringent matrix. This Jones birefringent matrix for linear birefringent fibers, so panda, bow tie, that was presented in the view graph already. So it can be diagonal. It is complex 2 by 2 matrix, and when the delta phi is induced relative phase retardation between orthogonally polarized eigenmodes. So this description just help us to understand the performance of the polarization maintaining fiber in terms of matrix equations. When we have a fiber circular birefringent, it's a fiber which can be, for example, twisted. So isotropic fiber twisted is circular birefringent, and that preserves circular polarized modes. We have the matrix of this type. Of course, we can observe nonlinear birefringence when, due to the fact that the fiber, silica glass fiber, is a nonlinear coefficient. It is not so high, but it accumulates along the path, and the path can be in kilometers. So we can also have a coupling between both polarization due to this nonlinear birefringence. So this effect known as a nonlinear birefringence, and this nonlinear birefringence can serve also for example, for diminishing the effect of dispersion or solidum trapping. And this is intensity dependent. As we can see, nonlinear phase accumulates due to this nonlinear birefringent coefficients and due to the length of the fiber, and couples both modes. So we call this cross-phase modulation, which is induced due to nonlinear effect between both polarization X and Y. And this is responsible for changes of the state of polarization at the output of the fiber. So the effect is important if we have, of course, long paths and the high input power, or just average input power and very long paths, so it can accumulate for a nonlinear effect. But just neglect this nonlinear effect and keep to the linear regime. And there is another approach, apart of Jones matrix approach, this approach which is called Müller-Stokes formalism, and it is more general than Jones approach. Why? Because it concerns all the types of depolarization, so not only totally polarized light when it is the case in the Jones matrix, but of course a partially polarized light which is due to the fact that the sources coupled to the fiber have limited coherence length. For example, laser diodes or other sources so can have limited coherence length. We can work only with helium-neon laser with a long coherence length only for labs, but in real applications we do have to take into account this the depolarization of the light. And in comparison to the bulk space, the Stokes vectors in fibers are related to the fact that they are called special Stokes vectors or special Stokes parameters. Why? Because at cross-section of the fiber, every point in the core of the fiber, so along the propagation length Z, and this fiber point, can have different value of Stokes parameters due to the fact that it's not a plane wave, it is a mode which is suspended into the fiber. So that is why in fiber we should replace the Stokes parameters analysis with special Stokes parameters analysis. And we can measure, of course, Stokes parameters due to very simple measurement by measuring at least 4 intensities in help of one polarizer and a quarter wave plane. So these parameters can be, of course, these devices can measure spatial parameters, but integrating it at the output of the fiber can give us idea about the Stokes vector value input and output of the fiber. This another approach to analyze the polarization, very suitable for analysis of performance of polarization fibers, Poincare representation. So there are commercially available devices which represent the Stokes approach, Stokes vector on the sphere, Poincare sphere, where the equator represents the states of linear polarization and both poles represents the states of circular left-handed and right-handed polarization, and the places between north and south represents elliptical polarization. So by matching the fiber just with the microprocessor-driven devices commercially available, we can make a realization of polarization performance, polarization evolution on the Poincare sphere representation. However, apart of polarization, there is very important issue, fact, within every biofringent medium, the effect of depolarization. So, depolarization effect, so measured by degree of polarization. So, the lower the degree of polarization, the higher the depolarization effect. So, can be derived from the Stokes vector approach. And we have a medium, biofringent medium, general biofringent medium, crystal of biofringent fiber. The two pulses, which can be spread into two polarizations, will be, after just passing through this medium, as you can see, will be displaced. And the measure of displacement is a measure of depolarization. This occurs due to the fact that the sources are of a limited coherence length. And this is very important when we, this issue is very important when we are working with the limited coherence length sources spectrum. And the higher the birefringence of the medium, the higher the depolarization effect. So this is also very important in analyzing polarization properties of the fiber. And due to the depolarization, the output part will have a lower degree of polarization, so higher the polarization range of due to the propagation. And we can also write this depolarization effect through birefringent medium based on Miller matrix equation. And a part of the, this is a Stokes vector on the input light, and this is the vector of polarizer, and this is of the birefringent medium. We should add the so-called depolarization matrix in matrix approach, which is responsible for the depolarization effect in order to obtain the light at the output of the fiber. So this gives us the idea of the depolarization ratio of the medium, and this depolarization matrix depends on the type of the source used. Either is it a gaseous laser or a laser diode or different sources, because they have different types of spectrum. For example, laser diode has a Lorentzian type spectrum, which PL parameter can be written as follows. However, Gaussian spectrum is, for example, for helium laser or gaseous laser, and this is different types. So this is very important from the first from the source and then for the birefringence of the medium point of view. Okay, so it was a general remarks about the polarization phenomena in optical fibers, in classical optical fibers, highly birefringent fibers, and now how to just go to the idea of polarization properties of the photonic liquid crystal fibers. So the first, as I presented on Wednesday, these fibers, liquid crystal fibers, are isotropic. Although the material inside is anisotropic, because liquid crystal is anisotropic, but due to the configuration, every single case is an isotropic case. So we do not have possibility to follow the polarization, to maintain the polarization in such fibers, because both propagation constants are exactly the same in x and y directions. Due to geometry of the system, so it is circular geometry of the system in planar, radial, and axial configurations, and there is no possibility to guide and to observe polarization. However, this fiber, which was proposed with elliptical core, had the possibility to guide polarization due to a special mixture of the fiber, but half of the power was lost, so half what we radiated out was leaky out of the, and only the power polarization produced along the AP axis was guided. So in that sense, this fiber was single polarization. However, due to the great difference between the silica glass and liquid crystal refractive indices, we had a lot of fiber modes, and this was a first representation of single polarization but multi-mode fiber. So, in the concept of liquid crystals, how to deal with polarizations, photonic liquid crystal fibers. Of course, when we took into account this first fiber, when the thermal tuning of the guiding mechanism observed, it was an isotropic fiber as well. And liquid crystal introduced here that was tuned by temperature to different band gaps, to different wavelengths, and then change guiding mechanism to the index guiding mechanism. But all the same, the orientation was planar, and still we had a fiber, isotropic fiber. The polarization could not be observed and could not be controlled. So in this sense, this is not good fiber for just dealing with polarization with this. There is also a possibility to just to play with reorientation of liquid crystals with a field, electrical field. And this is called dual frequency photonic liquid crystal fibers, which relies on the phenomenon that the anisotropy, the electric anisotropy, delta epsilon, can be frequency dependent. So for one frequency, the medium is positive, so delta epsilon is higher than 0 for another frequency negative. And it was also demonstrated in the concept of photonic crystal fibers infiltrated liquid crystals, and it made it possible to change the isotropic photonic liquid fibers into anisotropic by playing with only frequency of the external electrical field. But truly, anisotropic photonic liquid crystal fibers can be achieved by using highly birefringent photonic crystal fibers. And these are two examples commercially available. They are manufactured by Blaze Photonics. The first one we have purchased 5 years ago, and the second one by Crystal Fiber Company. And this is the fibers itself. They have, let us say for the first, they have well-defined birefringence axis. And the idea was to use these host birefringent photonic crystal fibers to interact with liquid crystals, to play with the polarization with liquid crystals. How it was possible to prepare such fibers to infiltrate? Well, that's a kind of teaching of infiltration. The simplest way is just to take this fiber, put into bottle with liquid crystals, and to make it infiltrated. But we can infiltrate it two ways. Total infiltration means all the capillaries will be infiltrated with liquid crystal, but there is also possibility to infiltrate selectively. So to infiltrate only big holes in order to have better control of polarization properties. So these small holes are infiltrated with liquid crystal, these big holes. And then we cannot splice the fibers with lead out and lead out, because why? Because splicing is a heating, and heating degenerates liquid crystals. So that is why there are different methods, for example, housing by extra capillary and put face to face to the leading fiber, or then just, for example, glue this total place, and we have a device to investigate liquid crystal, infiltrated photonic crystal fiber with guiding fiber. That is one way. Another way is also to make it coupled face to face without any housing. Experimental setup to investigate propagation properties and polarization properties in use also by controlling temperature and field. So it involves a small piece of the photonic crystal fiber, and this is module for temperature and voltage control, and enable also to make observation under microscope, or just to measure the output spectrum, or to make use of the polarimeter, which traces Poincare sphere representation. So it's exactly the device that can either measure tunable laser source at the input, and then the output, the device which can measure Stokes parameters and make it representation of the Poincare sphere. So it makes account of the polarization phenomena which occur in photonic liquid crystal fibers. When we infiltrate this polarization maintaining photonic crystal fibers with liquid crystal, we can totally infiltrate. We can also change the mechanism of propagation from index guiding or modified total antenna reflection to photonic band gap. And the results are visible here. And this is evident that the transmission spectra differ very much for this type of material use. So in that sense, the fiber can have also single polarization guiding. The polarization, which is in this red line, is guiding. We have two band gaps, and the polarization with perpendicular direction, orthogonal polarization, is nearly guided. So it is domination of. So it is good single polarization device. So which makes one single polarization. However, when we take into account this fiber, and the parameters of the fiber are the large holes. As you can see, it's relatively large because close to 5 micrometers, and the small holes close to 2 micrometers. And when we take this to the calculations, how would the impact of infiltrating separately with liquid crystals with big holes, nevertheless, what kind of liquid crystals we use. So it is important that we can tune the refractive index of this liquid crystal. So without changing the structure of photonic crystal fiber, we can tune the properties of the fiber due to the just changing temperature. As you can see, the process of manufacturing the photonic crystal fiber is very costly and very complicated. And in order to change, to put, for example, metal wires or another material, solid material, so it involves a lot of efforts. But here, when we put a liquid and we just tune with temperatures, refractive index, we have a lot of possibilities to observe polarization phenomena. So this is a simulation. So from the beginning, we started with simulation. It represents these big holes, represents the liquid crystal infiltrated, and we will change the refractive index of this material. Well, we start from 1, of course, liquid crystals has higher value, starting for at least from 1.4 and more, but we will see what we're doing. And this is a modal normalized light intensity at the output of the fiber, so modal field as seen in the output of the fiber. Let me see once more. It was too I don't know why it's just going too fast, but let us say so. We have to follow. You see, so this by changing the refractive index, we observe the situation. Then we arrive at the liquid crystal, and then with high refractive index, we can split the modes. So we can have from 1 core to 2 core fiber. So guiding will go, the power will go from the central core to the cores, liquid crystalline cores. So we have an inline splitter with the fiber. Okay, so it is simulation. So that is a view-gram what's going on in terms of liquid crystal refractive index and the birefringence. So we can tune birefringence. So we can change the effective birefringence of the medium, go to zero reverse sign, and split into these two guiding modes, two core fibers. So from one core fiber to two core fiber. And we can, by changing the refractive index, a lot of second order, third order, and higher order linear polarized mode will appear. So the structure will be much more complicated. Polarization is modal structure of the fiber is well more complicated. The most important parameter to characterize every highly birefringent fiber, a part of this bit length parameter, which can be measured as it was demonstrated in the view-gram, inversely proportional to the phase birefringence, we have group bit length and group birefringence. As you can see, group birefringence is related to phase birefringence, and it is a phase, exactly the phase birefringence for non-dispersive fibers, non-dispersive medium. But most of the fibers are dispersive, so this dispersion relation gives account to the group birefringence. So in order to fully characterize biopolarization properties of every anisotropic fiber, we should measure both these parameters, phase and group birefringence, or phase bit length or group bit length. This measurement is relatively easy. However, the group measurement is more complicated, and there are different techniques. One is wavelength scanning technique, which involves to find this group bit length due to this scanning of the wavelength. And to characterize the fibers, we have chosen this scanning technique, and this is you observe by just observing for different wavelengths of the fiber. You can have just characteristics, and you observe kind of intermodal birefringence beating for different lengths of the fiber, going down to the 7 millimeters. So this is the birefringence beating, and this is a parameter which we can measure, delta L, put into the group birefringence measurement. And by this, we could calculate this group birefringence, and this can be plotted. It is for photonic crystal fiber without liquid crystals yet, and for both fundamental mode and intermodal birefringence. And what happened that this is the result of the characterization of these parameters. And when we put liquid crystals in experimentally, what will be done by changing temperature, by tuning with temperature, we can reverse the sign of these both axes. So we can have this, the fiber is infiltrated only in a small part of liquid crystal, and this is the without liquid crystal, and this is with liquid crystals only these big holes. So only big holes are filled, and we can define the length of the liquid crystal infiltrated as L PLCF and L the total length of the fiber, the total setup components, in order to characterize the totality birefringence properties and also the birefringence properties of this small fiber. So what will be done by changing temperature? We can reverse the sign, change the birefringence axis as it was predicted theoretically. So slope axis can be just rotated 90 degrees. So we will make a fiber which will have a reverse side slope to fast axis due to the birefringence tuning that is responsible for infiltration of these big holes. I think we'll stop here for a break and we'll continue.
Questions? Other questions? Yes. Is there a limit to the length of fiber that you can capillary fill with the crystal?
The limit is practical because, you know, the longer the length, the longer does it take because it is a relatively slow process. You can also help with pressure, depending of course on the size of the greater the holes, so the filling is much speedier. The smaller holes under 1 micron is rather difficult. But there is no use to fill, as you can see later on, there is no use to fill for a long way because a short in section in say a few centimeters, it will be enough to make tuning and observe all the polarization phenomena. So there is no use to have a long path of infiltration.
But there's no idea of a fiber not that we can transmit light in a certain way over a long distance? Otherwise,
yeah, we can transmit. Well, the light is being transmitted as we can go. You can see there is a fiber, photonic crystal fiber, high battery fiber. The light is being transmitted solid core. So, and it's influenced at a short distance with liquid crystals which surrounds the core, solid core. And we need only this to manipulate the light, not to transmit light within the. We manipulate the polarization properties of the light due to the presence of liquid crystal.
How easy is it to control the length of this photonic liquid crystal fiber?
Yeah, we do it under microscope. We stop the process when we are satisfied, so we can put under the microscope and we control the process. And you want to, for example, 5 millimeters, 10 millimeters, or 15, so stop it and that's it.
But would we have some meniscus?
Yes, we have. Yes, we have, and this is a problem which occurs from very beginning, from the early 90s, when the people started to make the liquid crystal fiber. We have meniscus, and this is not here. It is not important. It was important only when there is propagation within liquid crystal, because due to meniscus we had a lens. We had a lens, and it was difficult to cut light into simply. But here, meniscus doesn't bother us because we propagate into glass. We propagate within the glass, and this meniscus, the fact that this meniscus doesn't have any influence on the light.
Are there more questions? Yes.
So when light propagates through a fiber, so what kind of polarization changes? Means its degree of polarization is also changing, or only its state of polarization?
Both. So state of polarization, when you have a source with a long coherence length, for example, helium laser, so you don't bother so much with diminution of degree of polarization. You can assume that the degree of polarization is constant as 1. But when you have a laser diode, or just lamp, just in photonic crystal fiber, use a broad spectral source. So the polarization is very important.
Like tungsten halogen lamp, suppose.
Pardon?
Tungsten halogen lamp, suppose we are using. A white light source we are using.
Yeah, so the polarization is very important. We should measure also the polarization.
Are there more questions? If not, let us thank our speaker. And since we are a little bit behind
fibers, these two values are different, and the group birefringence is wavelength dependent. That is why wavelength scanning technique is suitable to estimate, to measure this group birefringence. And we have in the fiber, we put liquid crystals into these big holes, but only to small part of the photonic crystal fiber. It means in order of 1 centimeter, few millimeters, or 1 centimeter. And the problem of meniscus or just coupling is not so important because the light is being coupled into the solid core, and the mode is suppressing the solid core. And of course, by increasing temperature, we can split into 1 core to 2 core fiber, and that will be the case when the index reflectivity will definitely very much increase. So we can reverse the birefringence axis due to the tuning temperature, so we can tune birefringence. And what will happen if we have the same fiber filled with a low birefringence fiber? Low birefringence liquid crystals. 1110 is a low birefringence liquid crystals with refractive indices, that is, ordinary refractive indexes, I remind you, lower than the silica glass. However, the extraordinary refractive index is the higher than the silica glass. And in that case, the whole spectrum is guided by the index guided. However, we observe the kind of beating periods of the spectrum change according to temperature. When we have different temperature, this is a change. And when we collect spectra for different temperatures, we can arrive to the case when this is a so-called a special wavelength at which there is no movement of the spectra, and this can be just explained in terms that the optical phase delay at this specific wavelength will be compensated. The optical phase delay of photonic crystal fiber will be compensated by the optical phase delay of the photonic liquid crystal fiber. So the big part of the non-infiltrated fiber, so the phase delay, will be compensated by a small part of the photonic liquid crystal fiber. This observation confirms our prediction that the infiltration with liquid crystals changes birefringence axis of the initially empty photonic crystal fiber. So the birefringence axis are reversed. So this is the observation of the compensation wavelength. And we can calculate this effect in terms of, by calculating the total fiber birefringence of the empty part, photonic crystal fiber, and the photonic liquid crystal fiber. And as we calculate it, and this wavelength dependence, we can finally arrive by this wavelength, the specific wavelength, compensation wavelength, to the fact that the group birefringence of photonic liquid crystal fibers is about 20 times or 23 times higher than the group birefringence of the empty fiber. It means that the section of the filled section, 20-meter section, compensates the section of 46 centimeters. So this is the answer why we don't need to use very long paths, infiltrated paths of liquid crystals, because its high birefringence is responsible for a relatively much lower birefringence of the photonic crystal fiber, and it makes possible to compensate the group birefringence. So this effect is, of course, tunable with temperature, because the temperature is this parameter which tunes birefringence in very high degree of liquid crystals and make it possible to the compensation of this group birefringence. So that is why this can be applied for a device to compensate group birefringence, so finally to compensate polarization mode dispersion by the part of the fiber which accumulates along long spans by traveling in telecommunication lines. So, and this can be drawn in these figures. That is a group birefringence of the empty photonic crystal fiber, glaze photonic crystal fiber, and this compensation part for different temperature. This was published 2 years ago in Measurement Science and Technology, how due to the effect of temperature-tuned birefringence, the birefringence axis could be reversed and compensated for a small this small section can compensate very much longer section to orders of magnitude or 20 times longer than these 5. So this is the idea exactly. It can be directly used to compensate, dynamically compensate differential group delay. Because imagine if we have a group differential group delay, so which is responsible, that is in time scale, there is a difference between both trains for both polarization peaks in X and Y, Z, and this goes to this compensating section, and this section can be either driven by temperature or also by electrical field, because electrical field will much more effectively change the orientation of the molecules, so finally will change the birefringence of the medium. So it should be a kind of feedback system. It is liquid crystals react in terms of milliseconds, nematic liquid crystals, but the problem is not so important in the time scale of speed, because these fluctuations of polarization, mode, dispersion, telecommunication lines are relatively long scale fluctuations. So, for example, this can affect vary from morning to the midday due to the just changes of temperature. So that is why this device, short pieces of this device, could relatively, in this speed of milliseconds, very easily compensate this differential group delay. What is about depolarization? So how it could be controlled when we operate with limited coherent sources length. So this can be also taken into account, especially in potential applications, and some investigations we have also made on depolarization properties in such a fiber infiltrated with liquid crystal disc, because in order to have the idea at what's going on, to make it consistent with numerical calculations. And this is a voltage applied to this plate, so voltage changes orientation, reorients liquid crystal, and that's why it changes birefringence of the fiber. And due to the fact that the sources, the light is partially polarized, so depolarization effect takes place. And there's a comparison of the depolarization properties of the photon-induced fiber. We can have an empty fiber, photon crystal fiber. We can have a classical highly birefringent fiber, and we can have photonic liquid crystal fiber infiltrated with two typical nematic liquid crystals, 5 Cb or 6 CBT, and depending on the azimuth of orientation of introduction of polarization to the axis of the fiber, we can have a great effect, a high effect of depolarization. So it must be this effect must be taken into account, because as the birefringent medium, every birefringent medium makes the polarization effect very important. And depolarization in this classical and photonic crystal fibers, due to the relatively low birefringence in comparison to liquid crystal birefringence, is not so important. This can be, the group birefringence can be also made in a special arrangement by using the method of estimation of a length, coherence length of the source. So the light can be split into two paths. Path A measures different degree of polarization is measured in this path A to calculate the coherence length of the source if we have a narrow band light source. Whereas by calculating this coherence length, we can use this coherence length to to measure group birefringence, just putting this coherence length. So this can be made by using the empty photonic crystal fiber or the photonic crystal fiber partly infiltrated with liquid crystal. So that's one of our latest suggestion how to already publish how to calculate this group birefringence in the photonic crystal fiber. And for the fiber-based photonics, this is calculated for and compared. The method was compared with traditionally used methods and with numerical simulation. Now I will go to a very hot topic, not published yet, although we have submitted a few days ago a paper to the Optics Express under consideration. This polarization properties of high-index glass-based photonic crystal fibers filled with nematic liquid crystal. So I will go to the extra presentation devoted to this topic. The problem is why we would like to use high-index photonic crystal fibers to cooperate with liquid crystals. So far, we have been using silica glass photonic crystal fibers. Most experiments were made from very beginning with lace photonics 1550, this with big holes photonic crystal fiber, recently with crystal fiber, and also some fibers manufactured in Poland. But silica refractive index, which is order of magnitude 1.46 or 1.45, so depending on the level, is lower than refractive indices of mostly liquid crystals. Most of liquid crystals have refractive indexes ordinary 1.5, extraordinary 1.7. That is why we have made a tremendous effort for the last 10 years to find a material with an index, liquid crystal material with a index lower than silica glass. And we did it 1550, 1110, but we sacrificed birefringence. So we had this index lower than silica glass, but the birefringence of material was very low. So we called it low birefringence. So we could tune mechanism of propagation with temperature, but it was difficult to tune it with electrical field due to the low birefringence. So we lost the basic property of liquid crystals, that is highly anisotropic, dielectric, and can very easily reorient. So that is why we had mostly propagation in majority of liquid crystals due to photonic band gap effect. What will be solution? If we could manage use photonic crystal fiber with very high refractive index in order of 1.9, we would have be sure that working with majority of liquid crystals, we will have index guiding material, index guiding structure. So let us compare what will be used. So with photonic band gap modes, these modes in our case, so it is not well confined as index guiding. And when we compare, so confinement losses connected that the light is being trapped within the core, the order of magnitude are 6 orders magnitude higher than for index guiding model. So that is why we started to think about use this, and there was a prototype fiber manufactured in Warsaw, in Poland, for multi-component glasses, and these are parameters of the fiber, so it has a standard as usual fiber 125 microns. Core diameter is about 10 microns, holes diameter 5 microns, so very easily infiltrated with liquid crystals, because in few microns regime, the process of the infiltration goes very well. Below 1 micron, rather badly, so you should force the molecules to go. But it is possible, but much more difficult. And the pitch, so the distance between the centers of the holes is roughly 7 millimeters. And when we compare the properties of this glass, at which was made this fiber, PBG08 glass, so you can see that it's close to 1.9. And when we compare with refractive indices of liquid crystal used, so all the refractive indexes are below. So that is why we have a situation, then we have an index guiding in all cases. So these are even materials which this 1679, it's a prototype liquid crystal material which have relatively very high birefringence, so from 1.456 to 1.86, so relatively high birefringence, and can be very easily influenced by external electrical field as well. So, first of all, we have made a theoretical simulations model of tuning when we applied to this liquid crystal infiltrated photonic crystal fiber, high index photonic crystal fiber, electrical field, and we assume, as usual, then due to without photoorientation, when we have without photoorientation, the process of infiltration with big holes goes usually in that way that the molecules go parallel to the axis of the fiber as is in the picture. It is a natural way of orienting of liquid crystals. It is a so-called flow-induced orientation. So molecules behave like swimmers who try to adapt to the conditions. So that is even without boundary conditions in a relatively few micron holes. And when we apply field, so the molecule starts to reorient, assuming that we have a Frederick's transition threshold, so it assumes to reorient. And this reorientation with increasing field will ultimately go to the situation when we have a perpendicular orientation, so we switch 90%. And this is, of course, dependent on the level of anisotropy. The higher anisotropy, the reorientation process. So we can have simulations and diagonal, in terms of diagonal tensor for planar, transverse, and just the situation in between, so-called angular orientation, when the situation in lower fields, and this can be modeled, and the situation by using the FAIR method with boundary, special boundary conditions, we can find birefringence changes. And these birefringence changes are plotted as follows in terms of wavelength. So what will be induced phase birefringence for given orientation? If we orient molecules 30 degrees, so the situation is for lower fields, so we can have a phase birefringence wavelength dependent as is seen. So for fiber orientations, we can increase the phase birefringence. So we can induce in the isotropical fiber phase birefringence, relatively high phase birefringence, and this is for a typical standard 5 cb calculation fiber with an isotropy 0.2. So we can arrive to very high level of phase birefringence within this fiber. And due to the fact that the high index glass will have always higher index than the surrounding medium, we will have very well confined both polarization. X and Y modes will be confined within the core of the fiber. So mode profile maintained in the whole wavelength tuning range, so independent on the wavelengths. And now you will see the experiment. It's not published yet, but this is due to the very low attenuation, we are able to guide for a very long distance infiltration. So as you can see, that's a distance sample length 15 centimeters. So 15 centimeters infiltrated with liquid crystal, it is possible to have a very nice guiding with very low losses. For silica glass-based fibers, we are few centimeters and the losses were high, so this is not possible. And here we have a sample length here from 15 centimeters, even more for mid scale. So due to the fact that the losses are very low. So this is very good propagation in such a photonuclear crystal fiber, and we estimated losses in the range of 1 to 2 dB. They are comparable to the losses of the bulk glasses of which the fiber is being made. And one remark, why these high index fibers are not in so popular use, because they have high losses. But for us, it's not so bad obstacle, because still we have a difference between refractive indices, and this enables us to propagate the light for at least 1 or 2 ranges of magnitude longer distances than in silica glass fibers. And this is a birefringence tuned experiment. That was based on, we observed on tuning of birefringence. So this is a Poincare sphere representation. So it means that by switching electrical field electrodes, we just observe evolution of a state of polarization. So you see this evolution of state polarization. So nearly goes for the poles. So it means the whole evolution. So the light is being polarization excites both polarization modes X and Y. And based on these results, we can calculate the difference in the phase change which is being introduced by the electrical field. So that's the difference between the phase change by initial value, final value minus initial value electrical field, E2, E1. So delta E, so it's a change of electrical field, and how this will influence the phase change within the fiber. So the phase change represents the bit-length parameter. So bit-length parameter really, as you can observe on the bit-length value, so it's exactly the change of 2 pi. And by having this phase change, we can calculate the birefringence change, which is being induced by electrical field. So this is relatively very high, and for different materials used, this is standard, 5CB standard, and this is with 1679 and 1658A, so this is material with enhanced liquid crystal birefringence. We observe very high tuning of birefringence in the fiber for a long distance, so we can propagate for even long distance. As you can see, this is material, classical material, and materials, liquid crystals with enhanced. So by choosing the appropriate voltage, electrical field, we can have a device which continuously tunes birefringence. So this is nearly linear change of birefringence. So the fibers, the devices with a linear change birefringence. So in this part, the very low losses, so the estimated losses for this comparable to the glass 1 dB per 10 centimeters. So in order 0.1 dB per centimeter. So it is at least 1 order of magnitude lower than with silica glass, enables us to manipulate with the fiber. And continuous tuning. Tuning is repeatable broadband for whole frequencies, for a whole wavelength, and we have continuous tuning devices. Just only tuning the voltage, and we can continuously tuning devices within the fiber. And this is a very important issue. The tuning range is proportional to the liquid crystal birefringence. And mode profile is maintained during the whole process. So this is the work which is brand new. And just coming back to my presentation, I would like to just show you one more application. One more application connected to the research with long period fiber gratings with liquid crystals. This research has been done together with a collaborating group in Canada, Photonic Research Center in Ottawa. And it is not exactly photonic crystal fiber with liquid crystal, but this is a long period grating. It is a grating. This is another topic I would like to just go on within much more, but it is devices which are written within the core and the fiber with long period, and they are specifically very popular for last few years as a very good sensors on the environmental parameters, gases and different types of substances, chemical substances. And what we have proposed that to this long period fiber grating we put liquid crystal around in order to have control of the properties of this grating and to enhance their properties. So this will be capillary use, and in this grating we can also have possibility of modify their properties by choosing the proper orientation of resonant frequency due to the liquid crystal. So this material, and in this sense we have used the steering electrodes which were infiltrated within the holes of the big holes of the fiber. So put electrodes and these electrodes in order to diminish the level of the electric field. So that would enable us to make it possible for steering wires in holes, and that's it. The problem of electrodes as steering is also a very important problem. In fact, that all the devices, photonic liquid crystal fiber devices, should be either steered by temperature or more affected by electrical field. And in order to diminish voltage, we should have electrodes close to the place when the liquid crystal is placed. Because when we have electrodes apart, 125 microns elongated distances, so the voltages will be high. And when you come electrodes close to the core of the fiber, so we can diminish the voltage, because the sufficient voltage to reorient the molecules is the order of magnitude single volts per micrometers. So in terms of the cross-section of the fiber, it gives us several hundred volts. But in terms when we just approach with electrodes close to the core, it gives us in terms of 10 or 20 volts. So that's a very important issue to elaborate. So it is exactly how this long period grating with liquid crystal from isotropic medium is being powered with changes properties, so the fiber is becoming anisotropic due to the orientation of the molecules, of the liquid crystal molecules. So this electrical field induces birefringence. So we'll have the long period fiber grating with birefringence, so well-defined polarization axis, and this can be sensitive not only for intensity but for polarization. So it is also one of the way to merging the liquid crystal with fiber optic devices. And as a conclusion, I think that I persuaded you that photonic liquid crystal fibers just create a so far perfect marriage couple to use these beautiful properties described by Professor Russell of photonic crystal fibers, and the majority of also beautiful properties of very many different properties and applications of liquid crystal. Thank you very much.
Questions? Yes?
In case of the depolarization, can we get the completely unpolarized light also?
It depends on the length of the fiber. Of course, you can go with the degree of polarization to 0, because the longer the nonlinear birefringent medium, the longer the polarization. Of course, the greater the depolarization, of course, depends on the source and on the angle of polarization introduced. You have 45 degrees is the highest depolarization, so you can achieve it in 0. So the light will become totally depolarized.
So after that, if the length is more than that, and after complete depolarization, it will again go for polarization, or it will what will that?
No, once you have depolarized light, you have nothing, so you can have any idea about. Of course, you can regain, you can reverse the signs, and we can. But once you lose the polarization, you are in the situation when there is just natural light.
Are there more questions? I have a question. So, we know that smectic liquid crystals, for example, would have much lower light losses because the thermal fluctuations of the reactor are suppressed. So, from this point of view, are there some good opportunities?
So far, nobody has used smectic. There are works of, we have been using nematic and also recently cholesteric or chiral nematic. And the other groups use also nematic and chiral nematic. Why? Because, smectic, there are layers, and the orientation is much more difficult to just to follow these layers. And nobody, it is not a flat, cell, it is a round geometry. Probably, well, we have also idea to try to just to have an idea what's going on with smectic, but so far I haven't seen the papers with smectic infiltration. And they are more viscous, so smectic are more viscous, so it would be much more difficult to infiltrate because we are.
Do it in isotropic.
Yeah. We have mostly we have doing in isotropic state, and we have cooled down. So because this is due to the viscosity, but well. Probably for our interest, we put sometimes we have a material which have also smectic phase when we just cool down. So probably we will check. But well, have not tried yet.
Are there more questions? If not, let us thank our speaker. And so we will now have a coffee break, and we'll meet here again at 3:30, so in about 16 minutes.